Ooh.
All right, guys, it's about 2 o'clock here, and I want to get to some questions, and I'll start rolling on. My name is Rahn. I'm a fellow Oaktable member. Did a tour of duty at Oracle for about 8 years in the Real World Performance Group under Andrew Holdsworth, and for the last 2.5 years, I escaped to the world of big data. So my talk today is about the current state of SQL and Hadoop. So just out of curiosity, how many people here are running Hadoop in their shops today? A couple. All right, well, and out of curiosity, what are you guys running for SQL on your Hadoop stuff? Okay, a couple different options. All right, well, I'm going to talk about a number of different things, but before I actually get into diving into the SQL and Hadoop stuff, I kind of want to take a little look at history, right? Because sometimes it's very important to understand where we've been to know why things are the way they are today and how far we've come along. In particular, I want to kind of look back about 8 years to the birth of Hadoop around 2006 and kind of revisit some of the technologies that brought us to where we are today here in 2014. As you may or may not know, it kind of all started way back in December of 2004, where 2 researchers at Google published a paper called MapReduce: Simplified Data Processing in Large Clusters. And in essence, what this paper was about was how Google was using a large number of commodity machines to build their inverted search index using this parallel programming paradigm that they called MapReduce. And it was kind of a crude but effective way for them to bring in lots and lots of data on a number of small machines, kind of crunch through it and build this index. And there were a couple people who were working on a project called Nutch and Lucene, named Doug Cutting and Mike Caffarello. And so basically they read this paper and had this idea, well, we could really implement this and this would help our search index thing. And thus was born Hadoop, right? So in 2006, around February, I believe it was, the Hadoop project kind of officially started, and Doug Cutting joined Yahoo to work on this there. So now I think, pretty much Hadoop has become a household name for more or less those of you with any familiarity around big data. So, it all started about 8 years ago or so, right? Now, a few years after MapReduce or Hadoop had kind of been out in 2008, 2 very prominent database personalities, Michael Stonebreaker and David DeWitt, had been running a blog while they're at Vertica, and this blog was actually called the Database Column, cleverly named after the organization of data in a column store such as Vertica. And one of the people reading this blog actually proposed a question to them of what they thought about MapReduce, right? And in response to that, they published this blog post entitled MapReduce: A Major Step Backwards. And what they basically went into in this blog post is that they were opining, obviously, from a database professionals and researchers state of view that there were a number of criticisms that they had about MapReduce. And in fact, it was actually very, let's just say, punchy, if you will. But I think it was also provocative in the sense that it did make people, think about things and kind of understand where it was MapReduce had come from, and in particular what the database community had been working on for like the last 25 or 30 years. And specifically, Stonebreaker and DeWitt brought up these 5 points that they kind of projected that the database community thought about MapReduce, right? And the first one of those points was that they felt that MapReduce was a huge step backward for the programming paradigm of large-scale data-intensive applications, right? And kind of what do they mean by that? Well, MapReduce itself is very crude, and it's a framework, right? It's more like a thing that you program on top of. It's not a declarative language such as SQL, where you just say what you want, and something else figures out how to do it. MapReduce, you actually had to implement yourself the how to do it part, right? They also were critical that MapReduce itself was a suboptimal implementation, meaning that it was always about brute force. There was no clever indexing, like you think of in a database, or even in general, speaking specifically to the public domain Hadoop, like even things like what Exadata has today known as storage indexes, right, which are basically data elimination techniques rather than B-tree type techniques, right? They also were critical that it really wasn't something new or novel at all, right? They said that this was just a kind of a crude implementation of techniques that have been in the database research arena for the last 25 years at the time, right? So it wasn't actually anything new in that sense. And they said that it was missing the majority of the features that modern and current database systems had, right? So it was not definitely challenging anything that was shipping in the market in terms of databases. Rather, it was really just a real bare bones type of thing. And in conjunction with that, it was incompatible with everything that is out there that most developers and business people interact with data with. Like, it didn't work with any of the tools, right? It didn't know how to speak SQL. It didn't know how to talk to Tableau. It didn't know how to talk to MicroStrategy or any of these things, right? It was really just a developer's tool and framework, right? So to summarize it, DeWitt and Stonebreaker basically said, hey guys, we think you're doing it the wrong way, right? This is, of course, January of 2008, right? Well, on rolls another year and a half, and there's a similar kind of comparison by Andy Pavlo and a bunch of other researchers at Brown that came and did a comparison of Hadoop, Vertica, and an unknown parallel database named DBMSX. And they kind of discussed in this paper, why use MapReduce when you can use parallel databases to do many of the same things, right? And they're extremely efficient and effective in doing those things, right? And obviously, again, this was coming from the point of view of database researchers, right? So it's going to be slightly biased, but it's biased for a reason in that sense, right? So they compared and contrasted a number of different problems in this paper and provided performance numbers related to Vertica, DBMSX, and MapReduce. Now, of course, most of their experiments, there's a factor of 100 or 1,000 that Vertica was better at than MapReduce. And so they kind of said, well, why use this thing that's 1,000 times slower, or you have to require 1,000 times more nodes to get the same performance out of it, right? They really didn't feel that was advantageous or beneficial to the marketplace, right? So, of course, you can't publish something like Stonebreaker and DeWitt did without having a little bit of rebuttal, right? That's what's kind of fun about that industry, and when you're at that level of expertise, you can be strong with your opinions, but in general, someone will have an equally and opposite strong opinion back, right? So the two authors of the Google MapReduce paper published a blog post, if you will, an article in the ACM Communications that basically was critical of how Stonebreaker and DeWitt were being critical of MapReduce in itself. But they argued that MapReduce was still useful, although they disagreed with their comparisons, that they were actually the right things to be comparing on. So they said, well, here, we're using it for things like machine learning and the index, or inverted index building, and a number of other things. And in fact, I think the number that was cited is over 10,000 applications at Google in 2010 were using MapReduce at the time, right? But the two authors also were critical of some of the public MapReduce implementations, right? So the difference here is that what Google was running as MapReduce was very different in the sense of implementation than what Hadoop was running as MapReduce, right? In particular, the authors were critical about startup latency, right? So startup latency was pretty large in the Hadoop domain, right? Because the engine that was running the MapReduce was not on usually. I mean, it always had to be invoked and started up each and every time. So there was like this overhead of startup costs, right? They also were critical of some of the data shuffling that had been going on behind the scenes. And they said you could do this better and smarter. Right? And another thing that they were also critical of was the format of which the data that was being processed, text data, right? I mean, I don't think it takes anyone with a PhD to realize that processing text data is very intensive, right? And if you have to do analytics on data, you hope that it's not text data, right? Because analytics, especially repeated analytics on text data, is extremely inefficient, right? And there was lacking, and MapReduce itself and Hadoop and the underlying storage was lacking natural indices, right? And again, by indices, we don't mean necessarily B-tree indices, but rather, log data and time series data comes in ordered form more or less, right? You usually don't get that much out of order. So when you're looking for a day's worth of data, there's a high and low value that you can essentially eliminate all the rest of the data to find, right? Much like Exadata storage indexes work today, right? So these were some of the points that they were critical of because they, more or less, said, we're doing these things with the Google MapReduce and in-house, but no one's doing this outside, right? You're still being very crude and using MapReduce like a mallet, right? So of course, fast forward 4 more years to June of this year in San Francisco at the Google I/O conference, where actually one of the Google employees came right out and said, hey guys, we don't really use MapReduce anymore, right? We stopped using it years ago. But here, if you look around the community, the Hadoop community, everyone is like into MapReduce right now. So they're kind of like, whoa, stop, we're not using it anymore. We've moved on to something different and better and more advanced, right? And so my point with kind of going through this story is that Google is obviously much further ahead than what the public domain and kind of Hadoop itself is. So to kind of use Doug Cutting's line, like Google sends us messages from the future, right? So they were basically saying, hey guys, MapReduce is yesterday's way of processing. We moved on to something better. Now, kind of in between all that, toward the tail end, Facebook had been running into big data processing problems, in 2007-8 timeframe. They had, petabytes of data that they had accrued and were processing terabytes per day. And they were using MapReduce, but found it extremely crude as well. So they started working on something that became known as Hive. And what Hive was a sequel to MapReduce translation, right? So it would kind of take more or less what looked like SQL and translate it into a MapReduce job, and then submit that job to run on their Hadoop cluster. Now, it's very, I specifically want to point out that Hive is not an execution engine in itself, right? It inputs SQL more or less, but outputs a MapReduce job. It has no execution part of it. The execution part of it is actually MapReduce itself. So in 2009, at the end of the year in August, the Facebook engineers presented at VLDB their story of building Hive on top of MapReduce here, right? So, they basically kind of mentioned, hey, SQL is extremely popular with our data engineers, so we wanted to help allow them to leverage this big cluster of computers and not have to spend a lot of engineering and programmatic time building MapReduce programs itself, right? So you kind of see SQL as showing up as being important even in a unstructured data kind of MapReduce / Hadoop world, right? Now, of course, they also realized that Facebook that the latency overhead was quite high with things like Hive and MapReduce. So in 2010, they started working on a new execution engine for SQL that was publicly announced in September of 2012 that was known as Peregrine. Now, the reason that Facebook started working on this engine was because they said that one of the most common complaints from their Hive users was that the latency was too high for interactive data analysis. Like, even the simplest queries take minutes or tens of minutes, right? So like if you're having to go and get a coffee every single time you submit a query to your Hive system, you get to be a little bit jumpy at the end of the day from the high caffeination, right? So anyway, the big problem with Peregrine is that it was only a single table aggregation engine, right? So what that meant is you couldn't do joins with it. but you could add up, things and count things and group by things, as long as all those things were in one table, right? And that actually got them by for some years, because when you have a big data environment, oftentimes you have just one big log table, right? And if you have a big log table, then you're kind of lucky enough to have everything together anyway. But that didn't last forever either, right? So in 2012, about 2 years ago almost exactly, at the Strata and Hadoop World in New York City, Cloudera came forward and announced that they had been working on this project called Impala. And Impala was an MPP-like query engine that was built to work on Hadoop. Now, unlike previous engines, other than similar to Peregrine itself, it was actually written in C++, as was Peregrine. So they decided, hey, we're not going to build upon this MapReduce framework because we think it's slow, it has lots of latency, it doesn't have the right operators that SQL constructs want to use, and so we're going to start and build it from the ground up, with a performance mindset, kind of like what Google was doing. In fact, the architect at Cloudera worked on the Google F1 engine while he was at Google. And of course, you can't go on without time with having another chime in from Stonebreaker. So now, in August of this year, Stonebreaker had another article in the ACM blog post webpage where he kind of mentioned, hey, is Hadoop at a crossroad here today, right? Because put simply, Impala is architected just like a shared nothing parallel database management system, right? Specifically, he noted that the MapReduce layer had been removed, and for good reason, right? It was slow, it didn't have low latency, or it incurred high latency into the pipeline. And as he mentioned, he had been pointing out for years, and some of his colleagues and other researchers in the database arena, MapReduce was not a useful interface when it came to SQL, right? And he was critical of Hive in particular, and noted actually, which was kind of a big compliment, that Impala was architected by savvy database management system developers who understood this pragma, right? And they were the development activity to Impala was also being followed by some of the other vendors in the area, or projects in the area rather. Hortonworks working on the Hive Stinger project, and Facebook working on what is Presto. And of course, in September this year, it couldn't have happened at a more timely time, but some researchers from IBM Almaden actually had a paper entitled SQL on Hadoop, Full Circle Back to Shared Nothing Database Architecture Systems. So here we are, 8 years after the birth of basically Hadoop, say 6 years after Hive was implemented, a number of projects have come and gone, and a number of initiatives are on the way, and we're almost right back to where Stonebreaker said we were going to be in 2008, right? So I don't want to say he told you so, but we're almost kind of right there, right? So I think it's actually kind of important to understand this lesson and why it actually happened, and some of the details that went along with it. So that's kind of the history lesson so far. So today, kind of quickly talk about a number of different SQL engines that are on Hadoop, and those I kind of have this tagline from NoSQL to NoSQL, right? And obviously, it's a little play on homonyms here, where no actually does truly mean not only, but I think that for the most part, not only really means no, as in zero, when you talk to most developers, but I think it's actually shown the business value that SQL actually has in organizations, and that has accrued over the last 30, 40 years, right? And so it's not just a technology that will fall away softly, and it has significant value to it. So first I'm going to go into some open source options. Actually, my build didn't work. Oh, wait. Okay, so Hive. So Apache Hive was originally developed by Facebook, as mentioned a little bit earlier, and is a sequel to MapReduce translation framework. Also, as mentioned earlier, it's notoriously slow, and currently in the ecosystem, Hortonworks is leading development and advancement of Hive. Particularly, they have a marketing project labeled Stinger that recently was delivered, and now, of course, you can't have a good, I'll come back to that one. So let's go into a little bit about Stinger. So Stinger had a number of different phases. There are 3 phases. Essentially, this is the point releases of Hive, moving from Hive 010 to 011, 012, and 13, the 3 phases. And in these 3 phases, they basically implemented a number of different optimizations into Hive. And one of those is including moving from MapReduce to Taze on Yarn, right? So Yarn is actually a new resource management, and Taze is kind of like the next generation MapReduce framework that kind of goes back and tries to fix some of these criticisms from the 2010 rebuttal from Jeff Dean on the ACM response, right? That they didn't have these low latency containers, etc., right? And as part of that also, they're addressing the text formatting problem, right? So they actually had to come up with a new file format, which is known as ORC, or Optimized Row Columnar. It's kind of like the next generation RC file, if you will. And it leverages some modern database processing techniques that were introduced probably around, say, 2010 or so, including vectorization, right? One of the big problems that Hive had been facing is that everything in the pipeline was a MapReduce job, and at the end of every MapReduce job, you write out all your stuff to disk, right? So when you have things like small tables in a star schema, or you want to essentially broadcast those tables, yeah, they would spill those to disk. So even if it was a few megabytes, so that in a short-running query adds a lot of latency, and so they basically implemented in-memory hash joins to solve that problem. They also introduced some new functionality, right? They had implemented window functions to help with analytics, and added a few other decimal types. Originally just kind of had hints and strings, and they added decimal, varchar, and date data types as well. So you can see that some of the more commonly used RDBMS features are creeping in to Hive in here as well, right? They currently do have subquery support as a checkbox, but it is extremely limited. In fact, I think you can only run one subquery. Like if there's more than one, then it doesn't work. And I don't believe it can be correlated either. So the other big challenge is that there is currently no anti-join support. So even in Hive 13, which is the current latest shipping GA version, you can't have a predicate that is an inequality, right? Which, of course, no one that does any data analysis actually do, right? So this is kind of a little bit of a architecture diagram from Hortonworks, kind of going over a little bit of this slide, the previous slide, and kind of from textual format to box and organization. They basically have, the base optimizations here in the upper left. They have the vectorized query engine that works in conjunction with buffer caching and stuff in the HDFS/Hadoop layer. They added some smarts to the query planner. They have also the Taze and Yarn components here, as well as kind of the analytics box, which I mentioned was kind of window functions and stuff like that. Now, there's been so many fix-ups in Hive that the Hortonworks team actually had a paper in Sigmod this year in June that goes into how they basically dealt with a bunch of the shortcomings that were in Hive. And if you're really interested in kind of like the nuts and bolts details of this stuff, I mean, this is a good paper to kind of pick up. Actually, I think, it goes into a number of different points. So kind of like high level, there are 4 points, plus or minus. One is that storage efficiency, right? So as Jeff Dean mentioned, analytics on text is kind of ridiculous. They moved and adopted the RC file format and moved from a row at a time or a tuple at a time type of serialization method to a vectorized processing model, right? They also implemented real data types, right? So if you store everything as kind of like an any type, you have to figure out what it is and convert it into a proper internal type every time you want to do data processing or math. Like you think about adding columns or grouping by columns, like that conversion takes a lot of CPU overhead, right? So moving to a more appropriate, strongly typed format helped as well. In addition, Query Planner, which was basically, not really much of anything, if you will. Probably, absent would probably not be an overly harsh word. But now they actually are trying to gather statistics about things and use those types of statistics into generating query plans. And also I mentioned from an execution perspective, using more of a vectorized model operating on a vector of values rather than tuple at a time. So of course, you can't have a good movie or a project without having a sequel, pun intended there. So the marketing team at Hortonworks came up with the overly cleverly named Stinger.next project, which is essentially after they delivered the 3 phases of the original Stinger, they had to come up with something else, so the Stinger.next was born. And this is essentially kind of to track the roadmap for like the next 18 months or so. Roughly speaking, I think they mentioned they're going to do a 3-phase approach again, which is how the first Stinger initiative was done. And some of the things that they're going to deal with here, they're actually going to implement ACID transactions. Now, that does not mean it's going to be a transactional database by any means. In fact, it's very, very almost the opposite end of that spectrum, right? So they're just trying to basically allow kind of a flip of a switch, if you will. So if you make updates or merge data in, that all the data can be merged in before everyone else sees it, right? So it's just kind of more or less, if you think about it like partition view swapping, that type of, but at a transactional level, right? They're actually implementing more of a cost-based optimizer using a framework called Optique. And this is kind of a pluggable framework. So it's actually also being used by another open source project called Apache Drill. The non-equi join problem is going to be addressed, so they're going to try to deal with that in Stinger.next. Actually add more subquery support, hopefully, actually enough where they have any subquery that can't be unnested. I'm not sure if they'll actually do nested loops if you can't unnest it, but at least the majority of subqueries that can be unnested actually get unnested in the planning. And they have a little interesting view on materialized views. They have this DIMQ thing, which basically stands for discardable in-memory materialized queries, right? And this is kind of, to use the tagline is not your father's or your grandfather's materialized views. These are essentially like in-memory materialized views that can be purged out if they need to use the memory for something else, right? So the design is still a work in progress, but obviously there seems to be a need or a desire to move data closer to processors and elevate data from rotating Rust into memory, right? And then they also are taking a page from the Jeff Dean rebuttal and moving to a daemon-based process for Hive to eliminate some of the startup. And of course, I'm not a big fan of this name, but like LLAP, which stands for live long in process. But anyway, in short, it's kind of like we're moving to a daemon, right? So that way we can just accept work and reuse ourselves. We don't have to do this, startup, shutdown type thing, right? Okay. Next, I want to quickly talk about Apollo. As mentioned earlier, it was open source in October of 2012. It did not build upon MapReduce. It was its own execution engine, and that execution engine is written in C++. And actually, it's pretty modern. I would say it's one of the more modern engines out there in the sense that it uses LLVM and code generation. So actually, it generates a lot of runtime things because at execution time, certain things that you don't know other than or prior, right? So you can kind of fold in things and run tight loops and basically really leverage modern processing as it is built to be today. Kind of like all the intrinsics from Intel, SIMD instructions, kind of all these things kind of play in, right? In addition, they realized that they were not going to build this and have it be successful if they were going to run on text. So they came up in conjunction with Twitter and brought forth the Parquet format, which is kind of a columnar storage for Hadoop, right? It's actually kind of a lot like the HCC compression in Exadata, where they basically have pages or blocks, if you will, and in that block, or compression unit is the nomenclature for Exadata. The orientation in there is column-wise versus row-wise, right? And then they use a number of different packing and encoding techniques to shrink and represent the data. And currently, based on what I know, it's the fastest open source SQL engine that's out there, which is kind of what it was built to be, and it's probably at least an order of magnitude or more faster than what the current latest Stinger Hive 13 is shipping. So to put it in perspective of Hive 10, which is kind of what Stinger measures against, they say they're 100 times faster than Hive 10, so Impala is probably like 110, 120 times faster than Hive 10, to kind of use the same starting point of reference. The other thing that's kind of interesting is that it's the fastest despite all the operators being single-threaded other than the scan operator. So when you're thinking of your tree, joins and stuff up the tree, these are all single-threaded per operator, right? The scan is multi-threaded, but the rest of the tree is all single-threaded. So at most, each operator can consume one CPU thread, right? And so it never really runs at 100% CPU utilization when you're running a query. So there's a lot of room left for them to advance that when they step up and actually do full multi-threaded pipeline. Okay, quickly kind of look back at what 1.0 Impala brought us. User-defined functions and aggregate functions. They have integration with Yarn. I guess it's kind of called admission control, which allows queuing and prioritization within a queue of queries. They introduced a decimal data type, which was also introduced in Hive. And in 1.2.1, if I remember correctly, last December, they brought in cost-based join reordering. So you don't have to use the ANSI 92 format, you can use the 89 format, and it figures out what order to do the joins are if you have, of course, statistics collected on your tables. Haven't gotten rid of that one yet. And also in CDH5, it can leverage in-memory HDFS caching, which actually is done via zero copy reads. So rather than using, the old Linux buffer cache, this actually is a kind of pin data in memory, and then the interaction between HDFS and Impala is zero copy reads. Okay, so 2.0 Impala is due out about in the next month or so. And some of the roadmap items that were on the feature list there, they're adding window functions, adding subqueries where previously Impala didn't support any subqueries. They implemented spilling so that they can do disk-based joins, and also incremental statistics, which obviously for those of you who have been on like 11G Oracle, you know what that means as far as time to collect statistics. Adding also some more built-ins as people have requested things, and some more data types, etc. So definitely is making progress there, 2 years in to the development pipeline. And then kind of looking forward to, I guess, 2015 or so. Kind of once we run past January. The interesting things that were on the roadmap, working on nested data directly, so that you can kind of query nested data, JSON type things, but probably stored in a non-textual format, i.e. Shredded and placed in Parquet files. And I believe that Pig is supporting this today. So it's just Impala is adding that. They have to add that to their execution engine. Some of the 80 or 92 or 2001, can't remember, role analytic functions, grouping sets, cube, etc. The basic sets operators, minus intersect, and interaction with HBase. So essentially you can put and get rows with SQL through Impala front end into an HBase backend. User-defined table functions. As I mentioned earlier, the aggregation and joins are all single-threaded, so they're looking at actually increasing the parallelism there. Parquet, in addition, is looking to add index pages, which essentially are high-low values to allow, kind of data elimination and searching directly in, and also S3 integration, which is a extremely popular feature for those people who are running in the cloud. Okay, so next on the agenda is Presto. This was announced a month after the Cloudera announcement of Impala, and Facebook basically said, hey, we're on like generation 3 SQL engine here. We had Hive, then we moved to Peregrine, and now we're working on Presto. And much like Impala, Presto is also not based upon MapReduce at all, right? It's its own execution engine, runs as a daemon. It's written in Java versus Impala being in C++, but they do leverage bytecode compilation for speed and throughput, right? But the interesting thing is they actually have these connectors, right? The concept is a little bit different with Presto, where they actually have a Hive connector, but they also have things like MySQL, Postgres, Kafka, Cassandra connectors, and I think there might even be work on an Oracle connector. So essentially you can run a distributed query engine on top of individual shards of these other data stores, right? Some of the interesting features with Presto, they have approximate queries, which are based off the BlinkDB technology from the AMP lab in Berkeley, which kind of allows time-bound or error-bound values to be returned. So you can kind of say, I want to return something at a 95% confidence factor, right? So it actually will start scanning your data, and when it thinks it has 95% confidence factor, it'll return it, right? So these are built into some of the aggregation functions in Presto. They also have a distinct limit optimization where you can kind of say select distinct limit n. So if you're only looking for a number of distinct values from a large data set, they can kind of push this down and quit early, so to speak. They also do support window functions, and they do have S3 support. So a couple weeks ago at the Facebook at Scale conference, Netflix talked about how they're using Presto in AWS on Parquet file format data. So they're definitely, if you're in the cloud in AWS, S3 support is kind of a big checkbox there. The other thing is they actually support a hyperlog data type. Now obviously this is probably not entirely surprising for those of you who have social media type data that you deal with. You have to do like monthly average users or monthly average views. So essentially you have this sliding window, and every day you count the number of unique visits, right? And then you slide the window one day and count them again, and you slide the window one day and count them again. And so you don't really want to have to go back and count them each and every time for every day you slide the window, right? So you can, very much like Oracle stores stats for incremental stats, you store each day's unique value in a hyperlog data type, and then you can aggregate them all at the end, right? So you only have to calculate the hyperlog in the most recent bucket or partition, and then you add in and do the approximation across all the other data types. So that's kind of a very nice feature as well. Okay, that brings us to the next one, and that's Apache Drill. Now, Apache Drill was actually announced just before the announcement of Cloudera's Impala, but it was nothing more than an announcement. It was basically MapR saying, hey, we're going to do this thing, but we don't have any code yet. So I think that was, in my opinion, just a little bit of the marketing machine getting out in front of Cloudera's marketing machine. But as a result, 2 years later, Impala is almost on version 2, and Apache Drill just basically shipped a pre-production developer preview grade version, right? So it's the most immature of the open source SQL engines that are out there that specifically I'm talking about today. As mentioned earlier, it also uses the Optic optimizer that is now being worked into Hive. But one of the different use cases for Apache Drill is that it's actually kind of geared more toward nested and semi-structured data without having to have metadata definitions, right? So you can kind of point it directly at a file or a directory, and it kind of does nested data schema discovery, right? The other difference I would say that Apache Drill is that unlike Impala, it did not try to inherit or start with the HiveQL-based subset of SQL language. It basically said, hey, we're going to be ANSI right from the beginning. So the SQL dialects aren't obviously compatible then, so you can't just migrate things if you're running, say, on Hive onto Drill until the things are actually ANSI compliant within Hive itself. All right, and that brings us to the next one. Okay, so the AmpLab guys kind of also have a little spin-off called Databricks, have a couple projects that they've been working on, Shark and Spark SQL. So originally Shark was a kind of fork of Hive 0.9 on Spark, and AmpLab had their own kind of cut point time release of this, and it was more of a research project than a enterprise product, if you will, right? So that has actually been abandoned and end of life, and I'll mention that in another point. But they also have this underlying framework, an execution framework called Spark, which is an alternative to MapReduce. So they kind of recognize some of these other things that MapReduce was limiting on, and they have things that basically allow you to store data sets in memory and pin them in memory. So they have these RDD data sets that let you pin stuff in memory, and they have integrated APIs with like Python, Scala, and Java. So This is actually a little bit different use case probably than, say, Impala. This is more of an integration into a language that allows you to access data via SQL within that language, right? So the framework itself is kind of more of like built to say, oh, I have some data I want to bring in, and I can do that with SQL, versus like putting Tableau or something like that in front of this. So in July at the Spark Summit, they, meaning Databricks, announced that they were end-of-lifing Shark as we knew it. They were introducing Spark SQL, which was kind of bringing in new functionality right into Spark. And then there was a new project to actually put Hive on Spark kind of officially, and the JIRA number here is 7292. So that's actually kind of like an official port, that makes it a first-class citizen to run on Spark for those people who want to run Spark as their framework and Hive as their translation level language. Okay, so that brings me to the kind of end of the open source stuff, and now I want to quickly dive into the closed source options that are out there. So the first one that was kind of announced in kind of an MPP format was Pivotal Hawk, and this was announced February of 2013, and essentially what Hawk was a port of GPDB to run on top of HDFS, right? The kind of advantages that brought is that you got kind of all the rich SQL that had been built up and a smarter optimizer over time with GPDB, but it actually offered less functionality than GPDB itself did because of the way that the catalog is stored in some of the underlying structures. So like it didn't support indexes or all the functionality that GPDB supported, but it allowed you to kind of run more or less a parallel database execution engine on top of data in HDFS. The initial release actually only allowed you to store data in the GPDB format, which was not an open format, so all the data that you had in your Hawk database was not accessible by any other execution engines in Hadoop, right? So you kind of had database locked in this file that no one else could access. But recently, they actually added support for Parquet. So now you can actually interact with Hawk, or Hawk can write data to Parquet, and other things can read and write that data too. The other thing that I mentioned here is that Hawk does require Pivotal HD, which is Pivotal's Hadoop distribution. So you can't necessarily just get Hawk and run it on top of your Cloudera or Hortonworks distribution, and you have to run it on top of the Pivotal distribution of Hadoop. Okay, of course the next one, Big Blue has their own version as well. They recently announced Big SQL 3, and I'm particularly mentioning Big SQL 3 here because Big SQL 3 was actually a complete rewrite of Big SQL. Big SQL is part of the IBM package of Hadoop, if you will. And the previous version of Big SQL was more like Hive, where it was a translation language to MapReduce. It had richer support than Hive did, but it was still running on top of MapReduce itself. So this is a completely new rewrite. It's its own execution engine also. There's no translation to MapReduce. It does have native file readers as well as leveraging the Java open source readers and writers, kind of the SERDES, if you will, right? So it can it has a handful of file formats that it can read natively, and if it can't, then it can kind of fall back to the Java-based SERDES ones. It does have rather rich SQL support. They do claim to be able to run all the TBC-DS queries without modification, and those include things like window functions, with clause, set operators, so it's a pretty big and sophisticated set of SQL that they support. And they claim to have a modern query planner, but obviously this is all new stuff, right? So they've kind of taken whatever they have in-house at IBM, whether it be DB2, Netezza, or Cognos. All these engines have some kind of SQL component to them, and kind of put them all together to run on top of HDFS and their Big Insights package. Most recently, an announcement was made at Hadoop Summit where Actian introduced Project Vortex, which is, don't get me started on the names here, which is actually using now a product called Actian Vector, which was previously known as VectorWise, which is the X100 engine that kind of came out of CWI as the vectorization engine behind 1ADB experiments that was later commercialized into VectorWise, and then that spinoff was bought by Actian. and then Actian renamed it to Vector, and then they had this project called Vortex. So I hope that wasn't confusing. Anyway, they have really rich SQL support because they've been around for since 2005 or so, I think. I'm trying to remember. They also are working on integrating with Yarn, which is more than just like saying I ported my database to run on top of HDFS. So they're actually trying to integrate with Yarn and use some of the resource management things with Yarn, which allows them to kind of scale up and scale down. I think they said they can kind of scale down to like 1 thread per data node at a minimum. And if you have followed any of the TPCH benchmarking, you'll recognize that VectorWise has every single node result top slot, right? So they are number one, at least number one, if not number 2, number 3, number 4 in every single node TPCH result, right? So they have a very fast execution engine, probably one of the fastest ones out there, and one of the more modern ones out there. But as a result, they also use their own columnar file format, which of course isn't shareable by any other engines in Hadoop. So if you want to not have 2 clusters, but have data kind of locked in your VectorWise stuff, this may be an option. If you want to know more about this, you can go out to YouTube and search for Peter Boncz, B-O-N-C-Z, and he has the video recording where he introduces this and goes into a lot of the technical details of how they implemented this. Okay, and you couldn't have a slide at Oracle related event without an Oracle slide. So Oracle announced their Big Data SQL in July, but really, it's not really a SQL engine at all, right? So it's really smart scan for HDFS. There isn't any SQL, or let me put it this way. There's as much SQL running with Big Data SQL as there is Exadata storage servers running SQL, right? In essence, they don't, right? They run selection and projection filtering, right? So that does allow you to send data back to your Exadata if you have also 12.201 or 12.102 and a BDA, right? So there's kind of a long list of things that you need there in order to make this work, but it is query only. You can't write any data. So it's done via an external table connector. So it's kind of more like a fancy connector than a dumb connector in that sense. And they had previously had a connector that they actually also did data type conversions on the remote side, and this obviously kind of does that as well too. But the problem is that this really only works if you want to filter a bunch of data and then bring it into your Exadata. If you actually have to join a data set that is in Hadoop with another data set that's in Hadoop, this is not a solution for you, unless that whittles down itself to a small enough amount of data that you can bring it back to your 8 database nodes in your full rack, right? And, now you have 18 machines working in your BDA as a full rack and 8 on your Exadata. So you can see that there's a little bit of lopsided compute power there. So just be aware of that. It's not really a strong criticism, it's just an informational thing. Okay, so that kind of brings me to a little bit of roundup here of the overall status of SQL on Hadoop. And I couldn't go through a whole slide deck without having at least one good meme. So SQL all the Hadoops here. So kind of like, how do you categorize these, right? Oracle and Teradata have kind of fancy connectors, whether they be, a specific connector name or like, in this case, the Big Data SQL thing from Oracle. You kind of have ports of commercial databases or their engines to run on top of HDFS in particular, and some are doing integration with some of the other things out there. Let's take the form of like old crusty Postgres or something more newer like VectorWise, but they do leverage their own proprietary file formats generally. And then you have kind of integrated but emerging, right? Obviously, it takes a while to build up all the features and functionality that something like Teradata, Oracle, IBM, or whatever has accrued over decades of engineering time and man hours. But stuff is coming along and it's progressing. So it's obviously a space to watch, but it's not something that you're going to unload your EDW with and go over to a Hadoop system and walk away with that today. Okay, so that brings me kind of to the end here. Have a cleverly crafted SQL statement to end the session. So if anyone has an awesome question, just let me know. And thanks for coming. No questions, guys? Say again?
Any update on the pig?
On pig? No, I only did SQL today. I mean, pig has made progress. They also are running on top of the Taze engine as well. They have integration with Parquet. So, anything else? All right, good. Okay.
What is your bet on the solution?
What is my bet on this? I bet it gets more interesting before it gets less interesting. Obviously, there's a lot of jockeying going on. I mean, I don't think that's pulling the wool over anybody's eyes here. It does take, building a SQL engine from scratch, or even like, starting with Postgres and trying to make something is not something that's done overnight. It's done over a number of years, right? So obviously, you can say that the emerging things like Hive and Impala or Presto don't support all the things that an enterprise data warehouse does. But obviously, they're running at scales that most enterprise warehouses do not, right? So it's kind of a lot of trade-offs in that sense. Like, can I trade off a bunch of these rich, robust features for a limited set at a larger scale? Now, the other thing too is that I'll guarantee that you won't get into any of these modern SQL engines from any vendor for $0 software cost, right? Things like Hadoop, Presto, Impala, and Hive are $0 software cost things. I mean, you can pay for support, but the acquisition for the software is $0, right? It's Linux and it's all open source, right? So that may be, attractive to some people too. Yeah.
So any comments on the future of HDFS itself?
Comments on the future of HDFS. Specifically, I don't think the HDFS API is going away anytime soon. The underlying code and the way it works, is obviously a work in progress. I don't know that it's going to disappear overnight. I mean, there are hundreds of petabytes of data locked in HDFS today, if you will, use the word locked. So, it has gravity, right? So I think people will work toward this solution or a solution around it. It's not like one of these things that they can just change direction overnight, because I don't know how long it takes to back up and restore an Exadata, but it probably takes a lot less time than to back up and restore or convert, a 1,000-node cluster, right? So gravity wins over time.
We are working on tiered storage for HDFS, but also develop SSDs and store disks and maybe some memory.
Yeah, so the comment is that there is tiered storage options being worked on for HDFS as well. Okay, well, thanks again, you guys. I'll clear the floor here to let the next speaker take up.